Hey everyone and welcome. Today we're tackling LeetCode problem 342, called Power of 4. The goal sounds simple, but there's a really neat trick to solving it efficiently. Let's break it down. The problem statement is straightforward. We're given an integer, which the problem calls n, and we have to return true if it's a power of 4, and false otherwise. This means we need to check if there's some integer x, where 4 raised to the power of x gives us n. Let's look at a few examples to make sure we understand. If the input is 16, the answer is true, since 4 squared is 16. If the input is 5, well, there's no integer power of 4 that equals 5, so that's false. And what about 1? That's true, because anything to the power of 0 is 1, so 4 to the power of 0 is 1. Now here's where it gets interesting. The problem asks if we can find a solution that doesn't use any loops or recursion. This is a huge clue that we should be looking for a clever mathematical property, or a bit manipulation trick, rather than just repeatedly dividing by 4. Even though the problem hints against it, let's quickly think about a loop-based solution. It helps build our intuition. We'd first make sure the number is positive. Then, we could just keep dividing the number by 4 in a loop. If at the very end we're left with 1, then the original number must have been a power of 4. And here's what that looks like in code. First, we have a check to immediately return false if n is 0 or negative. Then, the while loop does the work. As long as the number is cleanly divisible by 4, we divide it by 4. After the loop finishes, we just check if the result is 1. It's simple and it works, but it's not what the follow-up question was hoping for. Okay, let's tackle that no-loop challenge. The key is to find properties that are unique to powers of 4. The first major clue is that every power of 4, like 1, 4, 16, 64, is also a power of 2. This means if a number isn't even a power of 2, it definitely can't be a power of 4. So our first step is to check if the number is a power of 2. And there's a famous bit manipulation trick for exactly that. A positive number is a power of 2 if, and only if, the number n bitwise and n-1 equals 0. This works because a power of 2 in binary is just a single 1 bit followed by zeros. When you subtract 1, that 1 becomes a 0, and all the following zeros become 1s. Adding them together always results in 0. Great, so we can identify powers of 2, but that's not enough. Numbers like 2, 8, and 32 will pass our first test, but they are not powers of 4. So we need a second condition, a filter that only lets the true powers of 4 through. There are a couple of ways to do this, but one of the cleanest involves a simple math property. Let's examine the numbers again. If you take any power of 4 and subtract 1, look what you get. 1 gives you 0, 4 gives you 3, 16 gives you 15, 64 gives you 63. Notice a pattern? All of these results, 0, 3, 15, 63, are divisible by 3. Now, let's check if this pattern accidentally includes those other powers of 2 we want to exclude. What about 2? 2 minus 1 is 1, not divisible by 3. What about 8? 8 minus 1 is 7, also not divisible by 3. It works. This divisibility by 3 rule is the special filter we were looking for. So we can combine these ideas into a single, powerful check. For a number to be a power of 4, it must meet 3 conditions. First, it has to be positive. Second, it has to be a power of 2, which we verify with our bitwise trick. And third, the number minus 1 must be divisible by 3. If all 3 are true, we've found our answer. And here is the code for that logic. It's an elegant one-liner that directly translates our 3 conditions into code. We check if n is greater than 0, and if it's a power of 2, and if n minus 1 modulo 3 is 0. No loops, no recursion, just pure logic. Let's talk about performance. The looping solution's runtime depends on the size of the input number. We call this big O of log n. But our no-loop solution? It performs the same few checks regardless of whether the number is 4 or 4 billion. This is called big O of 1, or constant time, and it's incredibly fast. Both solutions use constant space, meaning they don't need extra memory. So to wrap it all up, the big idea here is that powers of 4 are just a more specific type of power of 2. By layering our checks, first a general one, then a more specific one, we can narrow down the possibilities. This problem is a fantastic example of how looking for underlying mathematical patterns can help you replace a loop with a much more efficient, constant time operation. I hope that breakdown was helpful. If you learned something, feel free to hit the like button or subscribe for more explanations. If you have a different way of solving it, I'd love to see it in the comments. Thanks for watching, keep up the great work, and I'll see you in the next one.